Okay, so we have studied linear kinetic energy, 1/2 mv squared. And so what we're going to do is talk about rotating objects, and because they're rotating, it won't just be mass, it'll be moment of inertia, and that will be kilograms meters squared. And instead of meters per second, it's going to be radians per second, angular. So instead of 1/2 mv squared, we have 1/2 IW squared. Now, mechanical energy will be conserved, and we're going to only look at conservative forces here. And so I know it's a little bit confusing when you look at conservation of momentum versus conservation of mechanical energy and wonder, well, which one should I use for which problem? The only time you're going to be using mechanical energy conserved really is if you have height, and that's going to work done by a gravitational force as a conservative force, and we're going to have conservation of energy because of that. So you're going to have problems where you either start with a velocity and then it causes some height change, or you're going to start with a height change and it's going to change into some sort of velocity, linear, and rotational. Because we have things like a bowling ball, or a pitcher throws a ball that's spinning and it's going linearly, but it's also rotating. So those are the kinds, that's when you're going to be using this formula, is when you have some height and you're changing that height into velocity or vice versa. Okay, so otherwise if you don't have that, don't use conservation of energy, use conservation of momentum. Because conservation of momentum, while it can't have any outside torques, it can have forces that work inside to change the mass distribution. All right, so if we look at this problem here, we have a solid sphere, we have a height of 2 meters, it's going to roll down, it has a radius of 0.75, has a mass of 3.25, I don't think we need the 30 degrees, and it's 2 meters high. Well, what we can say here is initially all it has is height, it's not moving. But when it comes down here, it's not only going to have linear, it's going to have rotational. It's going to be rolling and moving in a straight line and rolling. Now, the temptation is to throw values in here immediately, but let's see if we can make this a little easier, which we can. And because it's a solid sphere, I'm going to use 2/5 mr squared for the moment of inertia, because a solid sphere, if you look at your thing, is 2/5 mr squared. The other thing I'm going to do is I'm going to change that W into V over R. So that W squared is going to be V squared over R squared in this moment of inertia. All right, so as we look at this then, we have a mass in every factor, this being a factor, that being a factor, and that being a factor. Within this factor right here, oh, I wrote that wrong. It's supposed to be 1/2. I was looking ahead. And that 2 will cancel with that 2, and this R squared will cancel with that R squared. And so what you end up with here is GH is equal to 1/2 V squared plus 1/5 V squared. And you would just add the 1/2 plus the 1/5 together, and 9.8 times the height of 2, and then divide by 1/5 plus 1/2, and you end up with a velocity of 5.3 meters per second. Now if you wanted to have your angular momentum, you could easily just take your V and divide by your radius. So the radius here, V divided by the radius is going to be your W, and that would be radians per second. So it's spinning this fast and it's moving linearly this fast. It's asking for the linear speed, so there you have it. You don't really need to do W. Also, be careful with these problems because, again, this would be a problem here. I think, in fact, this is a homework problem, where you have this sled that's 215 meters away. It wraps itself around this pole that has a 0.3 meter radius. Starts out at a speed of 112. It's shut off, and then it goes 20 turns around the pole. So you'd want to go 2 pi r is the circumference times 20, and basically what you find out is that a lot of this rope is used up because now the sled's going to come over here and only have this radius. With this kind of problem, you're going to want to use conservation of momentum because that internal force of tension is affecting it. It's changing the mass distribution, but it's an internal force. No external forces and torques are being added, and so you can use conservation of momentum. You can't use conservation of energy here because the rotational kinetic energy actually increases because work's being done, and we really can't conserve something that's being added. So the conservation of mechanical energy will not work with this one.